1.5, the imaginary unit I. So some quadratic equations have no real solutions. To overcome this deficiency, mathematicians created an expanded system of numbers using the imaginary unit I, defined as I equals the square root of -1. All right, so here it says write as a multiple of I. So we know that the square root of 9, like this is basically, if you think of this, square root of 9, square root of -1. Well, the square root of 9 is 3, and then the square root of -1 is I. So that would be my answer. Here you have square root of 3, square root of -1. Well, I can pull out an I, but I have to leave the square root of 3. All right, 80, I got to break down. So then this, I have square root of -1, square root of 16, square root of 5. So then I end up with a 4i square root of 5. All right, so this next one, we're just going to simplify things as we go. So we have 5 minus, and again, remember, this is square root of 25 times the square root of -1. Okay, so here we have 5 minus 5i. Okay, we got to simplify this guy. So we have -4 plus, and here we have square root of -1, square root of 4, square root of 7. So we have -4 plus 2i square root of 7. All right, so I highlighted the answers just so that now you can see exactly what the answers to these questions were. All right, so some of our objectives is express square roots of negative numbers in terms of I, add and subtract complex numbers, multiply complex numbers, divide complex numbers, simplify powers of I. The imaginary unit I, again, is defined as I equals square root of -1, where I squared equals -1, right? Because if we square -1, the square root of -1, we're going to take away the square root, so just think about that. The square root of a negative number, so if b is positive real number, then the square root of -b, which is b times -1, equals the square root of b times -1, or square root of b, I, or just make sure you can see it, it's I square root of b. Complex numbers and imaginary numbers. The set of all numbers in the form a plus bi with real numbers a and b and I, the imaginary unit, is called the set of complex numbers. The real number a is called the real part, and the real number b is called the imaginary part of the complex number a plus bi. If b does not equal 0, then the complex number is called an imaginary number. Adding and subtract. We can add, subtract, multiply complex numbers using the same methods we use for binomials, remembering that I squared equals -1. So, for this first problem down here, we are going to literally combine like terms. So we have 5 plus 7 minus 11i plus 4i. So 5 plus 7 is 12. Minus 11 plus 4i is minus 7i. And that is our final answer for that problem. Okay. Over here, again, I'm going to work it down where I write things side by side. -5, do not get bamboozled by the negative. Plus 7i minus, again, do not get bamboozled by the negative. So then here, we have -5 plus 11 plus 7i plus 6i, which gives me 6 plus 13i for my final answer. So as you can see, all we did was literally combine like terms. It didn't matter that it was an I, it could have been an X, it would have been the same situation. All right, multiplying. Multiplication of complex numbers is performed the same way as multiplication of polynomials, using the distributive property and using the box. After completing the multiplication, we replace any occurrences of I squared with a -1. Okay, so for this first problem, we're distributing. So we get 12i minus 20i squared. Remember, I squared is the same thing as -1. So now this problem is 12i minus 20 times -1. So it is 12i plus 20. And if you're typing it in, 20 plus 12i would be in the form a plus bi. Okay. Now this one over here, I'm going to go ahead and do a box because that will make my life easier. So I have 7 minus 3i, and I have negative 2 minus 5i. So when I do that, I get negative 14 there. I get a 6i. I get a negative 35i. And I get a 15i squared. Okay? So as I'm working my way back up here, I have negative 14 plus 6i minus 35i plus 15i squared. So we're going to clean things up. And here we've got negative 14. This is minus 29i. And remember, this is plus 15 times negative 1. So then we have negative 14 minus 29i minus 15. So it ends with a minus 29 minus 29i. And that's my end result. All right, because the product rule for radicals only applies to real numbers, multiplying radicands is incorrect. When performing operations with square roots of negative numbers, begin by expressing all square roots in terms of I, then perform the indicated operation. So, we know this first one is square root of 3, square root of negative 1, and then we're multiplying by square root of 5, square root of negative 1. So, this first guy is I square root of 3, times I square root of 5. So then we got I squared square root of 15. That doesn't simplify. However, I squared, so is going to be a negative square root of 15. So yes, the product rule for radicals only works when both A and B are non-negative. For negative radicands, like you saw here, you must rewrite using I, because it does change your answer. All right, conjugates and division. The conjugate of the complex number a plus bi is a minus bi. The conjugate of the complex number a minus bi is a plus bi. Conjugates are used to divide complex numbers. The goal of the division procedure is to obtain a real number in the denominator. By multiplying the numerator and denominator of the division by the conjugate of the denominator, you obtain this real number in the denominator. What is the complex conjugate of the following? So, for this first guy, it is simply 7 minus 8i. For the second guy, it is 9 plus I. It is exactly that simple. And for this last one, so you got to think A equals 0, B is equal to 14, so it is a negative 14i is its conjugate. All right, and the reason why we learn about conjugates is for this reason right here, which is we're dividing and simplifying. So what we have to do is we have to multiply the top and bottom by the conjugate of the bottom. And you're going to see why we do this, okay? So the reason why we're doing this is so we can get a no I value in the bottom. So if I go ahead and do my box of the bottom term, because look, this is difference of squares, right? Then I get a 4, I get minus 10i, I get plus 10i, and then I get a minus 25i squared. And what happens here, you get 4, these guys cancel out, minus 25i squared, which becomes 4 minus 25 times negative 1, which is 4 plus 25, which is 29. So now my new denominator is 29, because I did that math for that reason. And then my top part, I'm going to do 7 plus 4i, 2, 5i. So we'll start working back here. We got 14, 8i, 35i, 20i squared. So we get our 14 plus 8i plus 35i plus 20i squared. 14, I can add these two together. That is 43i Remember, this is 20 times negative 1. So then I keep going. And I get, this becomes 14 minus 20 plus 43i. So then I am left with negative 6 plus 43i, which is what goes up here. Negative 6 plus 43i for my final answer. So the only thing you do next is you simply rewrite it as 6 over 29 plus 43i over 29. So you separate the real and the imaginary. So for this next problem, we are just multiplying by a negative 3i. So a little less steps here. So on the bottom, you end up with, you have 3i times negative 3i. So you have negative 9i squared. Negative 9 times negative 1 equals 9. Okay. On the top, we're going to distribute. And you have negative 3i times 5i minus 4. So this is negative 15i squared plus 12i. So this becomes negative 15 times negative 1 plus 12i. So 15 plus 12i. So I go back up here, and I get 15 plus 12i. Okay, I can already see in this problem we're going to do some simplifying. But here, you get, so for my final, okay, you get 15 over 9 plus 12i over 9. So then if I want to simplify that, I can divide this by 3, 5/3, plus I can also divide this by 3, 4i over 3 as my final answer. So yes, there's a lot going on with that, but that's what the final answer is for that problem. All right, so for this first problem, ideally I'm going to take the square root, x plus 5 squared equals the square root of negative 8. Well, we don't, until we learned about I, this now is x plus 5 is equal to plus or minus the square root of negative 8. So now we're going to start playing the game. So x equals negative 5 plus or minus, and this is now we know square root of 8, square root of negative 1. So x is equal to negative 5 plus or minus, we know we've got a 2i square root of 2. And that's the end of that problem. All right, so you could check this next problem to see if it factors, but we know the factors of 8, when both added, are 2 and 4, that doesn't equal 4, and 8 and 1, that doesn't equal 4. So that means quad formula, okay? So A equals 1, B equals 4, C equals 8. So we're going to plug it in. So don't forget quadratic formula, x equals negative b plus or minus square root b squared minus 4ac all over 2a. So I plug in my a, my b, and my c into the formula. And then we notice we have a negative 16 under the square root. So we're going to get our I. We know the square root of 16 is the square root of 16 times, or square root of 16 times square root of negative 1 equals negative 16. So square root of 16 is 4. Square root of negative 1 is I. So there we go. And now we're going to split it. But now I can reduce and get final answers of negative 2 plus 2i and negative 2 minus 2i. So quadratic formula does not go away. All right, additive inverse, if I use the example of 6 minus 7i, it is simply negative 6 plus 7i, so you're taking the opposite of both of them. But complex conjugate of 6 minus 7i, which we talked about earlier, is simply 6 plus 7i.